If you want to build native Android apps or dynamic web applications for use on Java Enterprise Edition server, you need to know Java. Hi, my name is Mohammad Rizwan. I am a software engineer with over 15 years of extensive software development experience. In this short course on Java technology fundamentals, I will show you how we can download and install Java Development Kit on Windows and how to get started with Eclipse, the free cross-platform IDE for Java developers. I will introduce the basic rules, syntax, data types, keywords, and best practices of the Java programming language. And since Java is a pure object-oriented language, I will describe how it implements concepts like encapsulation, inheritance, and polymorphism. Java is an incredibly consistent language. So once you understand how to think in the language terms, you will find that you can extend your tools and your capabilities very quickly. My goal for this course is to get you up and running quickly with the Java programming language by making heavy use of illustrations that help remember the key language concepts. I hope you will enjoy this course and do remember to subscribe to this channel to receive latest updates. So without any further ado, let's get started. So before we actually take our path down the road and download the necessary tools and went straight to coding, I think it is good to first have the principles of Java down. Java was built with a couple of principles in mind. The first among those is that Java is an interpreted language. Interpreted means that the Java code is compiled to a format that can be interpreted at runtime instead of compiling directly to the machine language. This is what makes the Java programming language portable across operating systems for which there is a usable Java virtual machine. Java Virtual Machine, or JVM in short, is a piece of software that enables the system to run Java programs that are compiled to some intermediate format. And in Java vocabulary, we call this format a bytecode. This distinction of acquiring the services of JVM for execution of programs makes the Java programming language platform agnostic. And for this, we normally use the term write once, run anywhere. Another important principle of Java is that Java is a pure object-oriented language. The object orientation in Java lies in the fact that everything in Java is an object. These objects model the real world objects. Like, for example, in my surroundings, I can see a couple of objects like a mug, an apple, a light bulb, and many others. So these objects have some state. Like in case of light bulb, it's off at the moment. That depicts its current state. And it has some behavior, like we can switch it on or off. So the current state of the object as well as the accompanied behavior that when triggered alter the object's current state by doing some internal processing is how we perceive objects in the real world. And Java is no different. In Java, we create objects that encapsulates state represented by its fields and behavior represented by its methods. We define classes as a blueprint from which individual objects are created. So consider this bulb class as a factory that produces objects of type bulb. And each object created this way manages its own state independent of others. We discuss more on the object-oriented aspects of the language later in this course. Java is robust and simple. The robustness of Java lies in its object-oriented characteristics. Applications are developed by making use of classes that each contains a set of fields and methods, and so the overall functionality is organized into coherent blocks that makes it easier for us to debug and to better manage and architect the overall application. Java is a multi-threaded language in a way that we can execute multiple programs at once. In fact, the JVM spawns and runs a special program in a separate thread besides the thread that runs our main program. And this special program basically manages the memory for us. so that we do not have to delve into explicitly managing it by ourselves. In Java vocabulary, we give a special name to this automatic memory management, and it's called garbage collector. When we create new objects in the application, the JVM allocates memory for us, and when we are done with the objects, the JVM kicks in and sweeps up the memory by destroying objects that are no longer referenced, resulting in recovery of the used memory space. Now let's talk about the Java runtime architecture. Shown here is a software stack that is used at runtime when we run the application. Below in the software stack comes the operating system. Java runs on a variety of operating systems, including Windows, Linux, Unix, and others for which there is a usable Java virtual machine. Right above it is the Java virtual machine that, among other things, is responsible to load the bytecode, interpret it, and execute the application. Further up in the hierarchy comes a Java class library, and it basically comes bundled with the JDK. More formally, we call it a Java core library, and this library makes the core Java classes available for use in our applications in order to speed up the development process. And finally, we have the compiled version of our application that sits on the very top. Now to install JDK on Windows machine, here is the checklist. We first have to download the JDK installer and later install it. Then we will be going to add the installation path to the system's environment variables. And finally, we will verify the Java installation. Let's do these steps one by one. To install JDK on Windows environment, we first have to download the installer from oracle.com by first searching the web for the term Java JDK download. Here we are presented with a couple of search results. Click the one from Oracle Technology Network, and here on this screen we can see a listing of all the versions of JDK with the latest one at the very top. At the time of this recording, the most recent JDK version is Java SE 15. It may have been changed by the time you see it. I have version 8 of JDK installed on my Windows operating system. So to follow along with this course, I would recommend to have the same version installed on your machine as was installed on mine. Scroll down a bit and you will see the version 8 of the JDK. Just click the JDK download link that is listed under Oracle JDK, and then you will be taken to a page that, if you scroll down a bit, is listing all the JDK installers for each operating system. I have a 64-bit version of Microsoft Windows operating system, so I have downloaded this Windows x64 executable. But if you are running a 32-bit version, Windows x86 is the right choice for you. To know which version of operating system you are running, go to the control panel, click System, and under system type you will find your version of operating system. Once you locate the installer based on your operating system, click it, and by doing so you will be prompted to accept the license agreement. You need to select this checkbox, and only then you will be able to click this button that will actually initiate the download process. As a side note, you have to have an Oracle account to download the executable. If you do not have one, just sign up for a free account. Once done with the downloading part, the next step is to install it. The installation process is fairly simple. Just double click the installer and accept all the defaults along the way. I have already installed it on my machine. The installation process not just copy over the applications that actually serves the purpose of compiling and running the Java programs, but also install the Java runtime environment as well. Once done with the installation, you can see that it gets installed somewhere inside program files. We have two different folders here, one for Java Development Kit and the other one for Java Runtime Environment. Java runtime environment kept within itself the Java core library as well as the Java virtual machine. Inside JDK, we have a bin folder that contains all the applications we need for development purposes, like Java C for compiling Java source code to bytecode, Java for executing the Java program, jar for consolidating the bunch of compiled classes into an archive with the .jar extension, Javadoc for creating documents out of the program comments, and many others. Next, we have to register the path to this bin folder to the system's environment variables that makes these applications accessible to us without referring the whole path each time we were to use it. So to register this path, copy the path to the clipboard, go to the control panel and search for environment keyword at the top right. Click on this link which says edit the system environment variables. Click on environment variables from this screen and look up for variable path under system variables. Select it, click edit, create a new entry and paste the path to the bin folder here and then click OK, OK and finally OK. Once done with adding the path to the system variables, the next step is to verify the Java installation. Open the command prompt by typing cmd on the start menu and type java space dash version and press enter. It says that the Java installed on my machine is 1.8.0 underscore 112, that is version 8 update 112. The last update part may differ on your machine because the Java version went through quite a few minor language updates, unless there are some major enhancements to the language features, in which case it releases a new version altogether. If you are presented with the Java version like this one, then congratulations, you have successfully installed Java on your machine. Next, we have to download the text editor that not just assist us in writing Java code, but also to help us out in compiling and running the Java programs. And I go for Eclipse IDE, the most dominant IDE in market today for Java developers that not just helped us out in writing code, but also to compile, run, and to do a bunch of other stuff all abstracted away from developers, and hence let us focus more on the work at hand and automate the tasks we are least concerned about. So to download the Eclipse IDE, go to www.eclipse.org/downloads, click download packages, scroll down on this page and under the more downloads link, click the link Eclipse Photon version 4.8. Once there, locate Eclipse IDE for Java developers and click the corresponding link that reflects your version of the operating system to initiate the download process. It takes some time to complete downloading, and once done, you will have a compressed archived folder downloaded somewhere on your system. Just uncompress the folder and you are done with Eclipse installation. When you explore the inside contents of this folder, you will see among other things an application with the icon of Eclipse placed in front of the application name. Create a shortcut out of it and place it somewhere on desktop or at some other convenient location so that you do not have to go deep inside the folder structure again to start the application. To create a shortcut, right click the application and click create shortcut. Cut this to the clipboard and placed it to some other convenient location. I have already created a shortcut and placed it on desktop. Just double click to start it and then it prompts you to provide the path to the workspace. The workspace folder basically tracks all the projects we created or otherwise imported inside Eclipse. with a bunch of configuration files that holds metadata for the projects. Just accept the default for now and click launch. If you open it for the very first time, you will have been presented with the welcome screen. You just have to close that screen and then the whole interface is made visible that we will be using throughout this course to create Java applications. But before heading towards it, I would like to discuss some configuration options that must be set ahead of time to be sure the Eclipse IDE is rightly pointing to the correct version of Java installed on your machine. Under Windows, Preferences, drill down on the Java Preferences, click Compiler, and check to see if it correctly reflects the one installed on your operating system. I have version 1.8 or 8 of Java installed, so under compiler compliance level, it should reflect the same. Also, under installed JREs, make sure the included entry is pointing to the right version as well. I think it is also good at this point to give you an overview of the Eclipse IDE vocabulary. Here we can see that the interface is split up into different sections. In Eclipse, we refer to these sections as views. These views basically facilitate the development of the applications by revealing aspects that we as developers would likely be going to dealt with during the development process. And the collection of these views are called perspectives in Eclipse vocabulary. For example, the Package Explorer view lists all the projects in your workspace. The Problem view highlights the issues in the code. The Outline view to locate and jump to a particular section in the application. The usefulness of the other views becomes evident as we go along. This is the main editor window where we actually write programs like we did in any other text editor. To maximize any view, just double click the tab and double click again to restore it back to its original size. If somehow your views get mixed up and you want these views to reset to their original position, from the menu, select Windows and under Perspective, simply click Reset Perspective. When we talk about Java, one thing that we must have to keep in mind is that everything in Java is an object. We design our applications by means of classes and further wrap the executable code inside functions or methods. To create a simple application in Java, we have to create a new Java project. Under the menu, select File, New, Other, type Java project here, select Java project under Java and click Next. A screen appears asking for the project name. I'm going to name it Simple Application, but you can name it whatever you want as long as it adheres to the naming conventions of Java. And the Java naming conventions dictates that the first character must be an uppercase letter, and there are no spaces or special characters in between. For each subsequent words in the name, I have used the uppercase first letter as well, though it is not required, but it is considered a good practice, a syntax sometimes known as a camel case. Below, it shows the location where this project is going to be stored. Next, it is suggested to let the Eclipse use the default JRE installed on the system for maximum portability. Accept the other configurations as is and move to the next screen by clicking Next. This screen very much gives you the build related details like where the source files and the corresponding compiled class files would eventually reside. So the source files went under src folder inside the project folder and the class files will be stored inside the bin folder. Once done, click Finish and a project is created for you with an empty src folder inside. Next step is to create a class file that will contain the application executable code. To do so, Right click on the src folder. Under new, click class. Here it prompts you to provide the class name, and the same naming conventions follows over here as well as we did when creating a new project. I name it main, but you can name it whatever you want as long as it adheres to the naming conventions of Java. Next, click the checkbox next to where it says public static void main with accepting arguments of string array. This will create a special method inside your class that is the entry point to the application and the one that wraps all the executable code inside that will get executed at runtime by the JVM. Click finish and a class gets created for you. Here is the class declaration. The keyword public tells the compiler that this class should be visible to other application classes. The keyword class re-emphasizes the fact that this is a class and it is followed by a class name that matches exactly the created file name, the part before the .java extension. The curly braces here mark the boundaries of the class, and inside the class we have a special method that will be looked up by JVM at application startup. This must exactly have the same signature or the keywords, like it should starts with public static void main with accepting arguments of type string array inside these parentheses and is further followed by a pair of curly braces. These curly braces basically wrap all the executable code inside. These are comments in Java and are ignored by the Java interpreter. All single line comments start with two forward slashes, and anything comes after these two slashes in the same line will be considered a comment by the interpreter and hence was ignored. These comments are basically meant to describe the reason of existence of the code snippets. You can remove it if you want to, but I am going to change it to say all executable code goes over here, to reveal the fact that this method will kept all the executable code inside. To the bare minimum, let's define a statement that prints hello world to the console. To do so, we need to make use of the classes that comes bundled with the JDK. Just type the class name system with an uppercase S and then type dot. You will be shown with all the fields and methods of this class. Choose out, which is an instance of print stream class, and this reveals the fact that one object may contain other objects within, as I will demonstrate later in the course. And after that, type dot and select the println method that takes string as an argument, and then type the string hello world in double quotes and end the statement with a semicolon. The dot here gives us the ability to peek inside the class for the required fields or methods and to select one by following the path inward starting from the main class. This is the simplistic Java class, unlike in other languages like Python, which takes only a single line of code to achieve this. In Java, however, everything is wrapped inside classes and further inside method blocks. Once done, click the drop down next to this green icon with right pointing arrow and select Run Configurations. You will be presented with this screen. This will allow you to create a new configuration for your project. Click Java Application and then the plus icon at the top left named New Launch Configuration, and a new configuration is created with the same name as your project name. We can configure the application from these different tabs, but for now keep it simple and just click the Run button. This will run your application and you will see the output Hello World in the console view. If you come that far, then congratulations, you have developed a simple console-based application in Java. Be aware of the fact that the console-based applications in Java adheres to the programming model where we have one class with a special method that serves as the entry point to the application. In addition, the classes we are using in this program are made available to us by the JDK. So to better understand what these classes offers to us, just double click the class name, go to help menu and click show contextual help. A help view appears. Click the link that says Java doc for java.lang.system and double click the help tab to maximize the screen to full view. Click method and here you will be presented with all the methods exposed by the system class. Once done with exploring all the details, click this cross icon to close this help view. One thing you should have noticed is that the compilation and the execution of the program is taken care of by Eclipse IDE and is abstracted away from us. Now let's see how it works manually if we were to compile and run this application from the command line. So right click the file main.java and choose Show in System Explorer. Click on the folder icon in the address bar and type cmd and press enter. This is a shortcut to open the command prompt from the path we are currently in. Type javac space name of the class that is main.java and press enter. This will compile your application and if all goes well, you will have a new compiled file with the .class extension placed inside the same directory as you can see here. Once the program has been compiled successfully, the next step is to run it. Type java space name of the compiled file that is main, but this time without the .class extension and press enter. The program runs and rightly so, it prints the output hello world to the command line as we did see inside Eclipse console. As with any other programming language, variables in Java are used to hold values. Java supports two types of variables, primitives and complex objects. Primitive type holds simple values while complex objects are used to hold instances of the Java classes. Primitives in Java can hold characters, booleans, variables that equates to either true or false, or numeric values, while every other type in Java is treated as a complex type, like string, date, and all others. Furthermore, Java offers a couple of data types to hold numeric values based on whether it's a whole number or it carries a fractional part, and also define the range of values one can hold, and it's up to us to choose them appropriately. There are total 6 of these types: byte, short, int, long, float, and double. The range of numbers each numeric data type can store are mentioned here, as well as the number of bits required to store data in memory. You will see that it is very common in programming languages to cast data between data types, like to convert data held by a variable of type int to one of other numeric types, like short or float. In order to convert the value of one primitive into several others, helper classes from the Java code library comes to the rescue. There is a helper class for each numeric primitive type available to us as depicted in this table. Besides conversion, there are a couple of useful utility methods these helper classes offers that one must be aware of instead of having to come up with his own implementation. The declaration of variables in Java is split up into three parts: data type, variable name, and the initial value on the right side of the assignment operator. Data type and variable name are required while the initial value is optional. So if you look at the figure on the left, you can see that we compare the declaration of variables for both primitives and complex objects. When we declare a primitive variable, we start with a data type, which in this case is int. The variable name is total employees and the initial value of 250. Java convention dictates that the variable name must be a lowercase first letter and there are no spaces or special characters in between. Down below is the illustration of the internal mechanics of how the variable gets bind to its assigned value. It is evident from the picture that a value of 250 is stored somewhere inside the memory, and this storage occupies 32 bits of memory primarily because the data type happens to be an int. Furthermore, you can see that each value stored in the memory has some address assigned to it. Just to give you a rough idea, consider the memory address as 00996577 that actually gives identity to the value 250. One thing worth looking at is that the variable name has a reference to the memory address instead of holding the actual contents as clearly depicted here. In other words, the variable total employees points to the memory address where the value 250 is physically stored. If we were to compare it with the assignment of the complex objects, you can see that the first two parts are the same. Declare the data type, which in this case is bulb with an uppercase B, and variable name is bulb with B in lowercase. The difference comes when we actually do the assignment part, which in the case of complex objects is to make use of the new operator to create an instance of the class and assign it to the variable. The new operator requires the object constructor next to it for instantiation. Don't worry if this object creation part seems daunting to you. We will discuss it in greater depth later in this course. Now let's come to how this complex object variable gets represented in memory. I would like you to pay very much attention to it because it reveals some important aspects of the Java programming language that you will shortly come across. As I stated earlier in the course, complex objects encapsulate some fields that represents their current state and some associated behavior that alters their current state as the business logic dictates. So for objects, all the fields enclosed within an object and the methods are likely to be stored somewhere inside memory, and the address to that memory location is copied over to the variable that holds that object, as we did see earlier for primitives as well. But the point that I would like you to focus your attention to is that the object scoped variables also hold references to its assigned values instead of directly holding those values within. It can be seen from the figure that the object bulb has only one field named state that holds a string value of reflecting the current state of the bulb, but instead of storing this value directly within, it actually holds a reference to the memory that have this value stored. I hope that this illustration will help you to more easily understand this concept, and it will definitely get pay off when we discuss about classes and objects later in this course. Since the assignment part is optional, the variables gets initialized with these default values in case we are not providing the initial value at the time of variable declaration. All numeric primitives will get assigned the value of 0. Boolean variables takes on the value of false, and complex objects are given the value of null by the compiler. Now let's jump to the IDE to see these variables in action. I have created a new project named variables and create a class main within that holds a single method named main that wraps our executable code as we already went through earlier. I have written some code to demonstrate the working of the variables. These are single line comments in Java and are ignored by the Java interpreter. To make a comment that spans multiple lines, wraps it around forward slash static and its flip side, static forward slash. Here you can see we have assigned the character A wrapped within single quotes to a variable grade of type char or car, however you pronounced it. Initialize the is of variable of type boolean to true or lowercase and assign literal numeric values to each of these numeric types. An important point to notice in this code snippet is the way the initial values are assigned to variables of type long, float, and double. You can see that we have appended L, F, and D to these values respectively. So here is the rule. The Java compiler considers each whole number as of type int and a value with the fraction part as of type double. So if we omit L from this value, you can see that the compiler complains about it. So we need to be explicit about it and tell the compiler that consider this literal value as long by adding the modifier L next to it. At this point, one may argue that if we strict to this rule, then why the byte and short data types are accepting values with no modifiers appended to the end? And the reason is that the compiler complains in two cases. Either the assigned value does not fit into the target data type or the value exceeds the range of int data type. So if I change this 33 to 330, it starts complaining because the max value held by byte data type is 127. Likewise, the value assigned to the long data type exceeds the range of int, and so we need to be explicit in that case too. Run it and you will see the output on the console. One thing forgot to mention earlier is that the plus operator works in the concatenation mode when one of its operands is a string. So it converts the other operands first to a string and then combine them all together to make a single string for printing to the console. Now let's talk about the conversion between data types. We have to look into it from two different perspectives, from bottom up or upward conversion and from top down or downward conversion. In the case of upward conversion, we are converting from the data type that have the smallest range to the one that accepts a larger range of values. So in this case, the conversion has been performed implicitly because there is no fear of losing data. But this is not the case for downward conversion. In fact, the compiler complains if you tend to do it this way. So in this case, you need to be explicit in your conversion and wrap the destination type inside parentheses to tell the compiler that I know that this operation might result in a data loss, but I want you to go ahead and do it for me. So the compiler now let you go through because it knows that you are well aware of the consequences this action might have resulted in. One side effect to this approach is that if the value assigned to the target data type overflows or exceeds its max range, then it wraps around and starts over from the beginning. So the results may surprise you in this case, as you can see here that we cast a value of 132 byte, and since the byte can hold a maximum value of 127 and 130 exceeds the byte range by 3, it wraps around and assigns the third element from the opposite side, and that is minus 126. So now let's move to the IDE again. I'm going to uncomment a few lines of code to reveal what we have just discussed. Besides these implicit and explicit conversions, you can see that we can also make use of the helper classes to convert data between data types. Here we create an instance of the integer helper class and pass the int value as an argument, and later call its double value method that returns the double version of the passed in integer. So before wrapping up this variables section and jump to the next one, I would like to highlight the importance of another built-in class in Java named Big Decimal. It is advised to use this class to perform calculations where high precision is required instead of making use of the primitive data types, because the way the decimal values are stored in the memory somewhat surprise you. Again, I'm going to comment out some part of the program while uncomment the one we haven't discussed yet. First thing to notice here is the red squiggly line under the class Big Decimal that we brought in from the Java core library. And when moving the cursor on top of it, it reports an error that Big Decimal cannot be resolved to a type. So to give you a little bit of context on this, the core classes from the Java core library that we utilized in our applications are organized into packages based on common class characteristics. These packages basically correspond to the folders on the file system that separates out the different classes based on its intent. To use these classes in our application, we need to tell the compiler about the package this class belongs to right at the very beginning of the file. And the Eclipse IDE makes it super easy for us. Place your cursor over the Big Decimal class and click Import Big Decimal from java.math package. And doing so will resolve the error, and an import statement is declared for us at the very beginning of the file. One thing worth mentioning here is that all classes from java.lang package are implicitly available to the application without us explicitly declaring its import statement. If we were to step out to use a class, that we have to inform the compiler by adding the import statement at the top of the file. To know exactly how this double value gets stored in memory, I am passing in as an argument when creating an instance of the Big Decimal class and call its toString method that provide us with the exact representation of this double value in memory. On execution of this program, you can see that the double value deviates from the one we are actually storing, and it does impact the values of the expressions that use this primitive value in its calculations. To overcome this problem, it is recommended to first convert the double value to its string counterpart by making use of double helper class, and then provide it to the Big Decimal class and later use this class to reliably perform highly precise calculations. Operators in the programming world are the characters or set of characters that execute certain operations. And Java is no different. Operators in Java falls into different categories, with each one served a well-defined purpose. The assignment operator is used to assign values to the variables, as we did see in the variables section. The math operators are used to perform math operations on its operands. These shortcut math assignment operators, as well as the incrementing and decrementing operators, are to be used in cases where we have to modify the values of the variables. The comparison operators for comparing values, conditional operators to evaluate multiple conditions that each comes out to be either true or false, and the ternary operator that shortens the if condition to do one thing if the condition evaluates to true, or to do something else otherwise. Furthermore, we have listed the operators by its evaluation precedence. The closer to the top of the table an operator appears, the higher its precedence. This means that if we have a statement that includes a couple of these operators, then these operators gets evaluated based on their precedence, with operators of higher precedence are evaluated first. Operators of the same precedence are evaluated from left to right, except the assignment operator that always evaluates from right to left. If we were to reinforce the evaluation of some particular operators first, then we need to wrap that sub-expression inside parentheses. Now let's shift back to Eclipse IDE to see these operators in action. I have created a new project named operators and create a class main within that holds a single method named main that wraps our executable code, as we already went through earlier. Here you can see the assignment operator where we placed the value to the right of the assignment operator and the variable we are assigning this value to on the left. Likewise, we have the mathematical operators as well that are performing some math operations on this variable and assign the resulting value to the variables on the left side of the assignment operator. Here is the shorthand version to increment the variable add value by 5. It's essentially the same as if we do it this way. Same stands true for other mathematical operators as well. Down below, we have the postfix and prefix incrementing operators that eventually adds 1 to the add value variable. Even though these two statements come up with the same end result, but the path the compiler takes to evaluate these expressions is a bit different. It will become evident from the output of this code snippet. You can see that we start off by assigning the value of 20 to both val1 and val2 of data type int. Then in the case where the incrementing operator is placed before the variable name, it first increments the value of val1 by 1 and only then will it be going to evaluate the whole statement. While in this case, the whole statement is evaluated first and the string gets printed to the console, and only after that the variable gets incremented by 1. Run it now and you will see the difference. The first line prints 21 while the second one shows 20, even though both val1 and val2 gets incremented by 1. Then comes the comparison operators for comparing values. The double equals operator evaluates to true if both values are equal or false otherwise. This evaluation is wrapped within an if construct that dictates that the inside code will only get executed if this expression evaluates to true, or else it will jump to the next statement following this code block that is wrapped inside curly braces. The exclamation mark equals equates to true if the operands do not match. The greater than and less than operators check to see if one operand is greater than or less than the other one. We can also check whether one value is greater than or equal to the other value by using a mix of greater than and equals operator, and likewise with less than and equals sign as well. The conditional operators make decisions based on a couple of evaluations. For conditional AND operator, for this expression to evaluate to true, all its individual sub-expressions must equate to true. If any one of these individual expressions evaluates to false, the overall expression will return false. Likewise, we have a conditional OR operator that returns true if any one of its sub-expressions returns true or false otherwise. Finally, we have a ternary operator that takes on the value of val1 if the condition is true, or else it will fall back to val2. Now, one thing worth mentioning here about the comparison operators is that they worked just fine for comparing primitive values, but for complex objects, you have to use the equals method provided by each complex object for the purpose of comparing two objects for equality. If we compare two objects using the traditional comparison operators, the equality is checked based on whether they are the same objects and not on the inside contents of these objects. Java provides us with a couple of ways to manage both ordered and unordered collections of data in memory. Ordered collections are used to store data that can be later referenced by its index position. Whereas in the case of unordered collections, the values are required to be explicitly tagged with unique identifiers or distinct keys that can be later looked up to get to the actual values. The simple array is the simplest implementation of the ordered collection in Java. Arrays in Java are of fixed length and can only hold elements of the same data type. This means that once the array is declared to be of some specific length, it cannot be changed at runtime. It can be seen in this illustration that we have an array that holds 12 elements, each one storing the name of the month in order. Since arrays are ordered collections of data, so we can make use of the indices to store and later retrieve data from the array. One thing worth looking here is that the indices starts from 0. So the first element in the array is at index position 0, second element at index position 1, and so on so forth. Down below, I have illustrated the concept of a multi-dimensional array that is also supported by the Java programming language. Consider a multi-dimensional array as array within array. So to reach out to an element nested deep within an array, we have to take our path inwards starting from the outermost array. So in this case, to refer to the element Georgia, we first have to look up for element stored at index 1 in the outer array, and then inside that element refer to the first array element by its index 0 to get to its value. In the case of multi-dimensional arrays, the outer array acts as a bucket to hold instances of the inner array elements and does not contain any values by itself. So in this case, the size of the outer array is 3 and each array element holds a reference to the inner array that is declared to be of size 2, primarily because we want to store US states with their capitals. Arrays in Java are of fixed length. It means that the Java compiler requires that the length of the array is to be provided upfront during its declaration and it cannot be changed at runtime. If the requirement is to have a more dynamic array that can be extended to store more elements at runtime, ArrayList from Java code library is worth looking at. ArrayList exposes an enriched API that we can utilize to store ordered collection of data that varies in size. Please be aware of the fact that the array list is making use of simple arrays under the hood, but the internal complexities of how this data structure deals with the intricacies of the array are all abstracted away from us. As you can see here, we have been presented with a couple of utility methods that allows us to store, retrieve, remove, and search for elements in the array list. You can see for some of the methods that we are providing the index position that further validates the point that these methods make use of simple arrays under the hood. As you can see that the array or the array list only stores a single value. So what if instead of storing values by index position, we need some metadata that provides us with a glimpse of the inside contents instead of blindly traversing the array for values? Java brought to us with a hash map construct that did exactly the same. It allows us to store metadata along with the actual contents, and this metadata is to be consulted to get to the actual contents. Take the example of an array that holds data about company employees. So each element in the array stores an employee object that wraps employee data like employee number, designation, salary, and other relevant details. So what if we are only interested in looking up for employee with employee number say 5? So in the case of arrays, we have to loop through all the array elements, and for each element through the loop, we have to check for employee number in the employee object, and only if we found the match, we will break out of the loop, or else we will continue looping until we found the match. Since employee number is unique for each employee, we can use it to tag the employee object. This way, we do not have to unfold each employee element for its ID. From the illustration, you can see that we have tagged the capital by its state. This way, if we were to look up for the capital of any particular state, all we have to do is to provide the state name to the get method of the HashMap API and it returns the associated capital. Let's now switch to the IDE to see these data structures in action. I have created a new project named data structure and create a class main within that holds a single method named main that wraps our executable code. This is the syntax to create an array. The data type comes first, followed by a pair of opening and closing bracket to tell the compiler that we are about to create an array. Then the array name, months in this case, and since arrays are complex objects, we make use of the new operator to create an instance of the array. And during instantiation, we are bound to provide the number of elements this array can hold inside brackets, 12 in this case, and each element is of type string. Once declared, we store values to this array using its index position. To retrieve the stored values, we simply pass the index position of the element in square brackets, and we are provided with the element stored at that index position. Here is the short form of declaring and assigning values in one line by wrapping the assigned values in a pair of curly braces. The length of the array in this case is inferred from these total number of elements. Down below, here is how we declare a two-dimensional array. This time we have to provide not just the length of the outer array, but the inner array size is required to be provided as well, as I demonstrated earlier. Likewise, to store data into and to get data out of this multi-dimensional array, we have to provide the index to both the outer as well as the inner loop. Then we have a declaration of the array list. This is the syntax to declare an array list. The data type is a complex object array list provided to us by the Java code library. Then the type of data that this array list is going to hold is wrapped inside these angle brackets, a syntax referred to as generics in Java vocabulary. And this way we will tell the array list implementation that we will be storing strings in this collection. Then, as with any other complex object, we make use of the new operator to create instance of the array list. Here you can see that the name of the class is followed by a pair of angle brackets. If you are using a Java version prior to version 8, you must have to explicitly provide the data type here as well. However, since Java 8, the data type is inferred from the declaration, so you need not to explicitly mention it here. Then we make use of different methods of the array list class to add, retrieve, and remove elements from the array list. Next, we have the hash map, and it is declared the same way as we declare an array list. The only difference is that we are now storing two values instead of one, since we are no longer relying on the index position to get to the stored values. And so in addition to the actual value, we need to provide some key as well that will be consulted later to get to the actual value. So the hash map stores the provided values internally as key value pairs. Java does not mandate the data types of neither the key nor the value to be of some particular type. You are free to store values of any data type as per your business needs. Here we are storing both keys and values as of type string. Then we make use of the hash map API to put, get, and remove elements from the hash map. Same we did for array list, but this time using the key to locate values instead of using its index position. Moving on, Java provides us with some looping patterns that provide us with the next value from the collection each time through the loop without exposing its underlying representation. We have a list iterator implementation to iterate over elements in the array list and iterator for iterating over hash map. For an array list, we get an instance of the list iterator by calling array list iterator method. And this method basically hands over all the array list elements to the list iterator object for the purpose of iterating over its elements. Then we employ a while loop that checks to see if we have any more elements left by calling hasNext method of the iterator. If it comes out to be true, we request for the next element using its next method and then print it out to the console and it keeps on looping until the hasNext method evaluates to false. And this happens after we surpasses the last element in the list. The iterator implementation for hash map does exactly the same thing. The difference comes in the way that we now have to choose from one of two values to iterate over, either the keys or the values. Here we are first using the key set method of the hash map to get all its keys, and we put those keys in a set. Set is basically a data structure that works the same way an array list does, but it imposes a restriction on its values in a way that all values must be distinct. Then we get an iterator by calling the iterator method of the set class, and further this iterator implementation exposes the methods with the same names as we look earlier for array list. So once we start iterating over the keys, how come we get to the actual values of the hash map? Here is how we do it. We call the get method of the hash map by passing in the key, and this returns the associated values, and then we make it a part of the string that will be printed to the console. Run the program and you will see the output gets printed to the console. Java supports a number of constructs that allows you to easily control the flow of your applications. Conditional blocks, switch statements, loops, and so on. Consider the if construct as a conditional block of code that will only get executed if the associated condition evaluates to true. The picture on the left dictates the working of the if construct. We want to evaluate the grade of the student based on his final score. So we are passing in the test score as an input to the if construct. It checks to see if the score attained is more than or equals to 90 by using the comparison operator. If this evaluation comes out to be true, then the grade of the student is set to A, and there is no need to go further and test for other conditions in the pipeline. So the control jumps to the next statement following the if construct by skipping all the other conditions that are defined as part of the if clause. However, if the score is less than 90, then the first condition becomes false and the control falls back to check the next condition in the pipeline, and so on and so forth. So what if we have defined a couple of conditions and none of them evaluates to true? So then in that case, we have a catch all block that will get executed if it has not been caught up by any of the above conditions. Also, I have emphasized the fact that all conditions following the first one, including the last catch all part, is made optional by the language by surrounding it with a dotted rectangle and label it with optional. We can see that this expression makes use of the comparison operator for evaluation, which in this case is greater than or equals to. But if the requirement is to make decisions based on the equality of the operands, then even though we can do it by making use of these if else construct, but the language provides us with another construct that offers us a more elegant way to do these equality comparisons, and we call it a switch statement as shown on the right. We passed in the number of the month to switch statement and we get back its string representation. One thing to notice here is that we are not restricting the user to supply values between 1 to 12, though the internal mechanics are only dealing with the finite set and treat all values other than 1 to 12 to be considered an invalid, and let them be handled by a catch all clause that will mark it invalid before passing it back to its consumer. So it would be nice if we could put a cap on the possible set of elements that can be passed in and evaluated by the switch statement. And for the same purpose, we are making use of enums, which is short for enumeration. It is created the same way we create a class, but is much more simplified, and it basically contains a finite set of elements. Now let's switch to the IDE to see these language constructs in action. I have created a new project named conditional and create a class main within that holds a single method named main that wraps our executable code. Here you can see the if keyword is followed by a condition that must be evaluated to true in order for this block of code to be executed. Likewise, we have other conditions as well, each one preceded by keywords else if. And finally, we have the catch all block that does not require any condition and will get executed only when none of the above conditions evaluates to true. So the first condition is preceded by if, and all subsequent conditions are preceded by the keywords else if. And these conditions are checked in sequence with the next condition in sequence will only get executed if the preceding condition evaluates to false. As soon as any condition evaluates to true, the program control jumps to execute the code wrapped inside these curly braces and then get out of the if construct by skipping all the other conditions in the pipeline. Here we are passing in the month as an int to the switch statement. And inside the switch block, we have a number of cases that each will be evaluated in sequence and match its value with the one provided in the input. As soon as the match found, program executes the associated code block, and once done, break statement is added to signal the compiler that I have found a match and done with executing the associated code block. Now it's time to jump me out of the switch statement to the next statement following the switch clause, and no need to evaluate other conditions. The default keyword here works the same way in switch as else did for if construct. This is the same version of the switch statement as we saw earlier, but this time we are passing in the string representation of the month and asking for its numeric value. This code snippet here depicts the working of switch statement with enums. We have created an enum and name it day. That includes a finite set of elements, in this case days of week, all in uppercase and each one separated by comma. Then we select one among those values by using the name of enum dot and one of the values held by that enum and assign it to a variable of type enum. Consider it a same way that an int data type can hold a range of values, and we can assign one of those values to a variable of type int. Pass this enum variable onto the switch statement, and for each case pick the values from the enum that are to be matched, but this time we need not to precede the values with the enum name. If more than one cases are doing exactly the same thing, then we can combine them all together like this. Run the program and you will see the logs printed to the console. To create an enum, right click on src folder, under new, click other, type in enum here and select enum under Java and click next. Give it a name and click finish. Once created, list down values all in uppercase and each separated by comma. This finally wraps our discussion on the conditional blocks from the Java programming language. Now let's make our way towards understanding the looping constructs offered by the Java programming language. These constructs helped us out to iterate over the collection data. I have illustrated the four looping constructs on this slide. Choosing one over another is merely a personal choice. This includes a counter for loop, for each loop, while loop, and do while loop. Let's discuss these one by one in the context that each is given an array to loop through that holds names of months. So the first one is the counter for loop. This loop starts with the assignment of a variable with initial value of 0, supposedly because the array elements starts at index 0 as we discussed earlier in this course. Then a condition is evaluated that either equates to true or false. So in this case, a condition is made that checks to see if the counter variable is less than the total number of elements in the array. If it happens to be true, we have to look up for month by making use of counter variable that reflects the current index position and prints the month to the command line. Then each time through the loop, we are incrementing the counter variable before evaluating the condition for the next iteration. So when we reach to the very end of the array, only then the condition evaluates to false, and in that case, the program control jumps to the next statement following the for loop. Next comes the for each loop, and it essentially does the same thing as the counter for loop. The only difference is that in this case you need not to track the index position of the array. We will be provided with the next element in the array each time through the loop by the for each implementation. Next comes the while loop, and it works exactly the same way as the counter for loop. The only difference is in the syntax we use to define one or the other. The do while loop ensures that the loop body executes at least once because the condition is evaluated only after first pass to the code block that is surrounded by the do while loop. Rest remains the same. So you can see that there is not much difference in the behavior of these looping constructs. Now let's switch to the IDE to see these loops in action. Here you can see that I have created a new project looping in order to demonstrate loops in Java. Further, I created a class inside named main, and it contains the special method main inside that wraps our executable code. So this is the syntax of the counter for loop. Here is the variable initialization. We named it I in this case. This is the condition. This is the code that gets executed each time through the loop. And here is the counter gets incremented. So recall the workflow I just have illustrated and try to relate it with this chunk of code to clearly get an idea of what goes where and the order in which these pieces are called. Please do it for each one of the other looping variants as well. Run it and you will see the output from all the looping constructs. Now what if we are not interested in traversing the whole array, but rather we would like to search the array for some specific element, and as soon as we find a match we need to get out of the loop and so not required to continue looping to the end. Also, there are cases where the requirement is to loop through all the collection elements, but each time through the loop, the inside code block may or may not execute to the end as the business logic dictates. Java brought to us a couple of branching constructs that does exactly the same thing. It provides us with the break keyword that signals the compiler to jump straight out of the looping construct to the next statement following the loop, skipping not just the code following the break statement from the current iteration but also terminate the subsequent iterations as well. Also, we are provided with the continue keyword that allows us to only skip the current iteration and move to the next one. Let's see these branching constructs in action. I'm going to comment out some part of the code and uncomment the one we haven't discussed yet. So this loop here is searching the array for integer 12, and as soon as it finds a match, it sets the variable found it to true and then breaks out of the for loop, and so the execution control jumps to line 52. This code snippet logs one string or the other to the console based on whether we found a match or not. Here we are traversing this string one character at a time, and we are only interested in finding the number of occurrences of letter P in the whole string. So each time through the loop, we first check to see if the character at the current index position is P, and we get to know about it by using the char at or char at method of the string class by passing in the current index position. If the character returned is other than P, then we need not to execute the statement at line 69 that adds 1 to the count each time it finds a letter P through the loop. So to skip over to the next iteration, we make use of continue statement in this case. Run the program and here are the results. 12 is found at index 4 beginning from 0 and only two occurrences of P are found in the string. Now let's move to discuss the object-oriented aspects of the language. The first in the list is encapsulation. This principle dictates that all complex functionality in the application should be hidden from the user. To better understand this concept, let's take the analogy of a coffee machine from the real world. To get a coffee out of the machine, all you have to do is to choose your favorite beverage and press the button next to it, and by doing so, the coffee is made available for you. So all the inner workings of the coffee machine are abstracted away from you and instead provide you with a simple and easy to use interface to interact with the machine. Think what happens if we were to understand the inner workings of the coffee machine, like how the different ingredients are blended together and in which order. Also, what if we were to specify the quantities of each one of these ingredients and only then we will be able to get a cup of coffee out of it? It is certainly going to be a mess. So encapsulation in the object-oriented vocabulary enforces the same rule that all complex functionality should be abstracted away from its users. We make use of classes and objects to achieve encapsulation in the object-oriented world. So what are the benefits gained when we break apart the monolithic code into classes as the logic dictates? The first and the obvious one is that it makes the code simpler and easier to understand since the code is now split up into multiple classes, and by doing so, each class hides its internal working from its users. Furthermore, it is now easier to locate and fix bugs because the scope of the error is now narrowed down to individual classes instead of us lingering around the monolithic code. To better understand the concepts of classes and objects, this illustration will help demonstrate it to you. Take the analogy of a bulb factory from the real world that manufactures and produces bulbs for its consumers. Once produced and delivered, each bulb manages its own life cycle independent of others. So it will never be the case that switching one bulb off is going to switch the other bulbs off too. So the state of each bulb is managed independently. In the object-oriented terminology, consider the class as a factory, or more precisely as a blueprint from which individual objects are created or instantiated. Once created, each object will have its own set of fields, which we call the instance fields, and a set of methods, which we call the instance methods. These are called instance fields and instance methods because they are bind to the individual objects and we have to consult these objects for their values. Another reason why we name it this way is because there are some fields and methods that only makes sense in the context of the class and not to individual objects. And we have to reach out to the class for their values. For example, in order to get a count of how many bulbs are produced by the bulb factory so far, we have to consult the bulb factory for these details and not have to consult the individual bulbs. Likewise, we have to reach out to the class to get a count of the total objects instantiated from the class. You can see that the production count field and get production count method are not available to objects as these are confined to the class and are not meant to be included in individual objects. In object-oriented vocabulary, we call the fields and methods that are available to class only as static fields and static methods respectively. So organizing code into classes help to encapsulate the object state and further abstract away the complex functionality wrapped inside methods. Only the developer who created the class will have to know the internal workings of the class. We as a consumer will not have to bother went inside the class code for details. We just have to call the exposed methods and get back the results as we discussed earlier when we talk about the analogy of coffee machine. Let's shift to IDE to see these classes and objects in action. Here you can see that I have created a new project objects in order to demonstrate the workings of classes and objects in Java. Further, I created a class inside named main, and it contains the special method main inside that wraps our executable code. In addition, I have created one more class named bicycle that is meant to encapsulate the bicycle state and its associated behavior. Notice one thing, that this class does not hold the main method within, as this class is not meant to be served as the entry point to the application. Instead, it is being instantiated and used in the main method of the main.java class. For now, I would like you to relate each and every piece of code in the bicycle class with what I have just illustrated. So these are the instance fields. These fields are declared the same way we declare variables. The only addition is that the data type is now preceded by the access modifier, which can be either public or private or protected package, which is the default in case we do not add any modifier to the variable declaration. This modifier tells the compiler about its scope. Private here means that this variable is only available for access within this class and is hidden from other classes in the application. Public means that any class in the application can have access to this variable. Protected means that only the class that declares this variable and all of its subclasses can have access to it. And the default is protected package, and this means that the variable is available to any class within the same package. As earlier stated, packages in Java are used to group common classes together based on certain characteristics. To include any class inside a package, we need to provide the package name during its creation. We are leaving it off up until now, but it is advised to always group your classes into packages. This is where you will provide the package name, and it is considered a good practice to create your package names with your domain name in reverse order, followed by the name of the application you are developing, separated by dot. Here you can see that I have declared the package with my domain name techweavers.com in reverse order, com.techweavers, and then dot followed by any name that reflects your application intent. I named it Java Training primarily because the project is made for training purposes. Also, we only need to check this checkbox for the entry level class only. For all other classes, this checkbox will remain unchecked. Here we declare the static field. To make the field static, we add the keyword static after the access modifier. Then here we have some special methods that have the same name as the class name and are named constructors in Java vocabulary. These methods have been referred to each time we create an object from this class, as we saw earlier in the variables section when we declare variables of complex objects. These constructor methods start with the access modifier followed by the class name. Java is a case sensitive language, so make sure that it spells exactly the same. Then we have a pair of opening and closing parentheses and have nothing inside it in the first version, but the second version accepts three parameters inside these parentheses, each separated by a comma. The values for these parameters are passed in during object instantiation. Think of these parameters as placeholders for the passed in values by the caller of the function. Then we have a pair of curly braces that surrounds all the code that is to be executed during object creation. So in the second constructor, you can see that we are setting all the fields with appropriate values upfront before the object is ever made visible to service any request. We prepend the instance fields with this keyword, and it basically refers to the current object. So this dot gear means set the incoming parameter value gear to the instance variable gear that pertains to the current object. So one may have looked at it and argued that isn't it that we are referring these fields in the context of the object that we are about to construct? So why is it that we are explicitly decorating it with this keyword to re-emphasize that these fields belong to the current object? The reason is that it works even without this keyword, but the problem arises when the parameter names conflicts with the instance field names. The parameter names basically shadows the instance field names in that case, and to deal with the conflicts, or even if there are no conflicts, it is advised to decorate all the instance fields inside methods and constructors with this keyword to make it clear that these variables are bound to the objects and not to the class itself. Here you can also see that we are incrementing the static field as well inside these constructor methods in order to increment the instantiated objects count by 1. We can define multiple constructors as long as they differ in the size as well as the data types of the passed in parameters. Likewise, we can use any constructor for object instantiation as per our needs. Beside constructors, the other way to initialize fields is by making use of getters and setters to get and set field values instead of exposing those fields directly to the other classes in the application. This way, we can limit direct access to the fields by marking them all as private and only get these fields exposed via appropriate getters and setters. This data hiding part has the added benefit that we can define additional checks inside these setter methods to restrict the scope of the values the fields can be assigned to. Adding these getters and setters to the Java classes is so common that Eclipse provides us a quick way to define these methods. Place your cursor next to where the constructor methods are defined. Right click on the class, choose source and click Generate Getters and Setters. Select the fields that you want to generate getter setters for and click Generate. This will result in adding the getter setter pair for each selected field. You can also observe that we do not have the setter method for ID, primarily because we are setting the ID field from inside the class, and so there is no need to expose this method to the other classes in the application. Furthermore, we have defined two methods here, apply break and speed up, that basically alters the current state of the bicycle in terms of increasing or decreasing its current speed. Now let's switch to the main class that creates an instance of this class inside the main method by making use of the class constructor that accepts three parameters. So here we are passing in the arguments in the exact same order the bicycle class constructor method is accepting. So to jump to the constructor method from this main class, in order to know exactly the order of the parameters, hold down Control key on your keyboard and click on this constructor method. You will be taken to the constructor method that will get called. Now these are called parameters, and the values that we are passing in when calling this constructor method are called arguments in Java vocabulary. To jump back to the caller, click this left pointing arrow and you are back to the class calling the constructor method. Next, you can see that we are changing the speed of the bicycle by making a call to the method speedup and also apply brakes by calling apply brakes method that reduces the speed of the bicycle by the given amount. So the speedup and the apply brakes are methods of the class bicycle that acts upon the object state as the business logic dictates. Execute the application and you will see the results. Now let's discuss about methods in more detail. Methods in Java are used to group multiple statements together into a coherent block of code and further give it some sensible name that should reflect its intended behavior. Once defined, this block of code can be executed from any part of the program by simply making a call to the method by its name. Wrapping code this way and calling it from different parts of the program also makes the code reusable. This way, we do not have to write the same code each time we were to use it in our application. The declaration of the method comprises of two parts: method name and its signature. The chosen method name should be very much self-explanatory and it should reflect the served purpose. The Java conventions for naming methods are the same as we did follow earlier for variable names. That it should start with a lowercase first letter and there are no spaces or special characters in between. The signature of the method covers the number and type of arguments that it accepts inside parentheses. The body of the method then makes use of these arguments in its business logic. Furthermore, the method name is preceded by a couple of modifiers. It starts off with the access modifier, which can be one of public or private or protected package, which is the default. This signals the compiler about the method scope in the same way we did see earlier for fields as well. Labeling the method with the access modifier is optional, but it is sensible to include one for readability. If the access modifier is missing, it defaults to protected package, which means that this method is visible to all classes within the same package this class belongs to. Next, we have to mention the return data type from this method. Here you can see that we are only changing the state without sending anything back to the caller of this method. We need to be explicit in that case too and mention void to reinforce the fact that this method is only meant for changing object state and is not returning anything to its consumer. Here you can see that we are returning string from this method by including a return keyword followed by a space and then string that we need to pass on to the caller of this method, and further marked the return data type as string to let the caller of the method knows. Now let's discuss about methods in more detail. Methods in Java are used to group multiple statements together into a coherent block of code and further give it some sensible name that should reflect its intended behavior. Once defined, this block of code can be executed from any part of the program by simply making a call to the method by its name. Wrapping code this way and calling it from different parts of the program also makes the code reusable. This way, we do not have to write the same code each time we were to use it in our application. The declaration of the method comprises of two parts: method name and its signature. The chosen method name should be very much self-explanatory and it should reflect the served purpose. The Java conventions for naming methods are the same as we did follow earlier for variable names. That it should start with a lowercase first letter and there are no spaces or special characters in between. The signature of the method covers the number and type of arguments that it accepts inside parentheses. The body of the method then makes use of these arguments in its business logic. Furthermore, the method name is preceded by a couple of modifiers. It starts off with the access modifier, which can be one of public or private or protected package, which is the default. This signals the compiler about the method scope in the same way we did see earlier for fields as well. Labeling the method with the access modifier is optional, but it is sensible to include one for readability. If the access modifier is missing, it defaults to protected package, which means that this method is visible to all classes within the same package this class belongs to. Next, we have to mention the return data type from this method. Here you can see that we are only changing the state without sending anything back to the caller of this method. We need to be explicit in that case too and mention void to reinforce the fact that this method is only meant for changing object state and is not returning anything to its consumer. Here you can see that we are returning string from this method by including a return keyword followed by a space and then string that we need to pass on to the caller of this method, and further marked the return data type as string to let the caller of the method knows that it should expect a string from this method. So all these methods we discussed so far are the instance methods that belongs to individual objects and will only get called from an instance of the class. But what if we were to define methods that lives in the context of the class itself and are not meant for individual objects? To distinguish class level methods from instance methods, we need to add the static keyword right after the access modifier, the same way we did for fields as well. Defining method this way will then be called directly from the class definition instead of invoking it from an instance of the class. We can call one method inside another in case one method depends on the output of the other method. And in that case, we should have to remember one rule, that static methods will only be called from other static methods, and same is true for instance methods as well. Also, Java gives us the provision to define multiple methods with the same name as long as they differ in their signature, that is the number and type of arguments they receive. In object-oriented vocabulary, we give a special name of defining multiple methods with the same name but with different signatures, and it's called method overloading. One of the questions we have to answer with any programming language is whether the arguments we passed into the method are passed by value or passed by reference. Let's understand what these terms means. Passed by value means that the method actually creates a new local copy of the variable for each argument it accepts. This way, we are simply cut off from the actual variable and started working with the local copy within the method code block. On the other hand, passed by reference means that instead of making a new copy altogether, the code inside the method block points to the original variable, and this has the consequence that any modifications made to the values of these variables inside the method block will have a global impact and hence resulted in modifications to the actual passed in variables. In Java, variables are always passed by copy. Don't panic if all we discussed so far seems daunting to you. I'm going to further elaborate this concept by making use of this illustration. Here you can see that we are comparing both primitives and complex objects side by side, since we can pass both the primitives as well as complex objects as an argument to the method. Let's focus on the primitive part first. Here you can see that we have declared a variable named total employees of type int inside class company and set its initial value to 250. Later, we call method adjust employees, passing in the variable total employees as an argument to this function. This total employees variable holds reference to the memory address that stores the value 250, as we discussed earlier in the course when we talk about the declaration of variables in Java. Down below, we have defined a function that takes a parameter of type int, and since we know that the variables hold references to its value, the reference to the value 250 is passed to this parameter as an argument. But since Java adheres to the pass by value principle, a new implicit variable is created by the JVM with the same name as the parameter name, and it further goes on and initializes this local copy of the variable with the actual value taken from the passed in reference. So a new local variable gets created with the name employees count of data type int with an initial value of 250. Then we alter the value of this variable to 200 inside the method, and you can see that only the variable employees count gets affected by this change. The variable total employees have the value 250 retained. Please note that the naming conventions for defining parameters are the same like we did for variables, and the scope of these variables are limited to the method in which they operate. Once the method finishes executing, all local variables are available to be garbage collected. It is also absolutely fine to give the parameter the same name as the argument. Now, understanding this concept for complex objects is a bit tricky. Here you can see that we have a method readBook that requires the use of parameter bulb for its execution. Inside the method block, we turn on the bulb by making a call to the turn on method of the bulb object, supposedly because reading a book in a dark night requires the bulb to be switched on. This method is called from within the main method that creates a new bulb instance. Turn it off by explicitly calling the turned off method and then pass that object on to the readBook method. So again, as we see in case of primitives, a new copy of the bulb object is created implicitly and the existing state from the past in bulb object is copied over to the new object. And any changes to the local copy of the object inside the method won't get reflected in the original passed in object. So far, so good. Now comes the trickiest part, and our earlier discussion on this will get payoff now. If you remember, we discussed in our earlier talk that the fields of the objects hold references to the memory address that stores the actual contents and not directly containing the values within. So even if we are creating a new object altogether, the internal variables that we copied over from the actual object still refers to the same memory address, and so changes made to the fields of the local copy of the object gets reflected in the other object too, even though they are completely separate objects. This somehow confuses the developers and they come to conclude that the primitives are passed by value, but the complex objects are passed by reference, and that is not correct. Both primitives and complex objects are always passed by value. Now let's talk about the remaining two object-oriented concepts, inheritance that it should expect a string from this method. So all these methods we discussed so far are the instance methods that belongs to individual objects and will only get called from an instance of the class. But what if we were to define methods that lives in the context of the class itself and are not meant for individual objects? To distinguish class level methods from instance methods, we need to add the static keyword right after the access modifier, the same way we did for fields as well. Defining method this way will then be called directly from the class definition instead of invoking it from an instance of the class. We can call one method inside another in case one method depends on the output of the other method. And in that case, we should have to remember one rule that static methods will only be called from other static methods, and same is true for instance methods as well. Also, Java gives us the provision to define multiple methods with the same name as long as they differ in their signature, that is the number and type of arguments they receive. In object-oriented vocabulary, we give a special name of defining multiple methods with the same name but with different signatures, and it's called method overloading. One of the questions we have to answer with any programming language is whether the arguments we passed into the method are passed by value or passed by reference. Let's understand what these terms means. Passed by value means that the method actually creates a new local copy of the variable for each argument it accepts. This way, we are simply cut off from the actual variable and started working with the local copy within the method code block. On the other hand, passed by reference means that instead of making a new copy altogether, the code inside the method block points to the original variable, and this has the consequence that any modifications made to the values of these variables inside the method block will have a global impact and hence resulted in modifications to the actual passed in variables. In Java, variables are always passed by copy. Don't panic if all we discussed so far seems daunting to you. I'm going to further elaborate this concept by making use of this illustration. Here you can see that we are comparing both primitives and complex objects side by side, since we can pass both the primitives as well as complex objects as an argument to the method. Let's focus on the primitive part first. Here you can see that we have declared a variable named total employees of type int inside class company and set its initial value to 250. Later, we call method adjustEmployees, passing in the variable total employees as an argument to this function. This total employees variable holds reference to the memory address that stores the value 250, as we discussed earlier in the course when we talk about the declaration of variables in Java. Down below, we have defined a function that takes a parameter of type int, and since we know that the variables hold references to its value, the reference to the value 250 is passed to this parameter as an argument. But since Java adheres to the pass by value principle, a new implicit variable is created by the JVM with the same name as the parameter name, and it further goes on and initializes this local copy of the variable with the actual value taken from the passed in reference. So a new local variable gets created with the name employees count of data type int with an initial value of 250. Then we alter the value of this variable to 200 inside the method, and you can see that only the variable employees count gets affected by this change. The variable total employees have the value 250 retained. Please note that the naming conventions for defining parameters are the same like we did for variables, and the scope of these variables are limited to the method in which they operate. Once the method finishes executing, all local variables are available to be garbage collected. It is also absolutely fine to give the parameter the same name as the argument. Now, understanding this concept for complex objects is a bit tricky. Here you can see that we have a method readBook that requires the use of parameter bulb for its execution. Inside the method block, we turn on the bulb by making a call to the turn on method of the bulb object, supposedly because reading a book in a dark night requires the bulb to be switched on. This method is called from within the main method that creates a new bulb instance. Turn it off by explicitly calling the turned off method and then pass that object on to the readBook method. So again, as we see in case of primitives, a new copy of the bulb object is created implicitly, and the existing state from the past in bulb object is copied over to the new object. And any changes to the local copy of the object inside the method won't get reflected in the original passed in object. So far, so good. Now comes the trickiest part, and our earlier discussion on this will get payoff now. If you remember, we discussed in our earlier talk that the fields of the objects hold references to the memory address that stores the actual contents and not directly containing the values within. So even if we are creating a new object altogether, the internal variables that we copied over from the actual object still refers to the same memory address, and so changes made to the fields of the local copy of the object gets reflected in the other object too, even though they are completely separate objects. This somehow confuses the developers, and they come to conclude that the primitives are passed by value, but the complex objects are passed by reference, and that is not correct. Both primitives and complex objects are always passed by value. Now let's talk about the remaining two object-oriented concepts, inheritance and polymorphism. Inheritance is all about reusing the existing class features in other classes. This way, all the common functionality is wrapped inside a class, and the reason of existence for this class is primarily to package up the common features and make them available for other classes to add more specialized features on top of it. Java vocabulary, the class that exposes the common functionality is called the superclass, and the classes that inherit that functionality are called subclasses. So here in this figure, you can see that we are bundling the features that are common to bicycles into a bicycle class and let the specialized bicycle classes extend their common features from this bicycle class plus adds their own. So you can see here that the mountain bike adds suspension property in addition to what was made available to it by the bicycle class. And similarly, the road bike class adds specific tire width property. Now let's switch to the IDE to see this inheritance in action. I have created a new project named inheritance and create a class main within that holds a single method named main that wraps our executable code. We have created three more classes in the project. Here is the superclass bicycle that encapsulates all the common functionality inside, and then we have the more specialized versions of the bicycle class, each extending the bicycle class by making use of the extends keyword right after the class name and further followed by the name of the class this subclass is extending functionality from, which in our case is the bicycle class. By doing so, all the fields and methods of the bicycle superclass are made available to its subclasses as if they are defined as part of the class. Be aware of the fact that the constructor methods are specific to classes and are only meant to be used for constructing objects, and so these methods are not anticipating to the class features. And since we emphasize that only the class features will be taken down to the subclasses, constructor methods do not fit the criteria and so will not be inherited. But we have been given the provision by the language that we can call the superclass constructor methods inside the subclass constructors, primarily to initialize the variables that we brought in from the superclass by using the keyword super followed by the arguments in parentheses. Since we are passing three arguments here, the superclass three arguments constructor will get called. And once the superclass constructor is done with the initialization part, the control flows back to the subclass constructor where we initialize the fields that are specific to the subclass. One thing you noticed in the subclasses, we have defined the method print description in both subclasses even though we brought in the same method from the superclass as part of the inheritance. The reason is that there are cases where the subclasses needs to make some tweakings to the existing inherited features as per their needs. This is where the method overriding kicks in. If we are not happy with the inherited method, we simply provide our own implementation of that method inside the subclass. If the requirement is to simply add to whatever was made available by the superclass method, we can call the superclass method from the subclass the same way we did call the constructor method of the superclass, but the syntax is a bit different. This time use the keyword super then dot and followed by the name of the method. The add override decorator here is for readability purpose only. It can be omitted, but it is considered a good practice to explicitly mark the overridden method this way. An important concept that I would like to discuss here is that all the classes bound to the inheritance model are interchangeable. By this, I mean to say that we can construct objects from subclasses and assign them to variables of superclass, and the same is true the other way around as well. Creating an object of the superclass and assign it to variables of any of its subclasses. I would like you to recall the earlier talk where we highlight two different avenues of dealing with the conversion between numeric data types. We summarized that we have an upward conversion that is meant to cast value of smaller range to a data type that accepts a larger range of values, and we agreed that the casting in that case is done implicitly because there is no fear of losing data. Then we have a downward conversion where we need to be explicit and wrapped the target data type on the right side of the assignment operator to tell the compiler to do the conversion even though it has the consequence of losing data. Same rule implies for objects as well that are bound in terms of their inheritance relation. So as illustrated in the figure on the left, the mountain bike is the subclass extending from bicycle, its superclass. Also, if a class is not explicitly extended from any other class, it implicitly extends the object class that is made available to us by the JDK. So in our case, since the bicycle class is not extending any class, the superclass of the bicycle class is object in this case. So in the case of upward conversion, the subclasses can be casted to its superclass without doing anything special here. We created an instance of the mountain bike class and later assigned the reference to that mountain bike object to its superclass bicycle. This has an important implication in a way that we are exposing the functionality of a subclass via its superclass. And since we are storing reference of a subclass inside superclass, calling any method of the superclass will actually call the method of the subclass, eventually adding a more dynamic behavior to the application. And this is what we call polymorphism in object-oriented vocabulary. For downward conversion, we need to be explicit and wrap the subclass inside parentheses to tell the compiler about our intent. Here you can see that we are doing upcasting to put object of a subclass to a variable of a superclass and downcasting as well. Run the program and you will see the results. Java adheres to the single inheritance model. This means that a class can only extend from at most one superclass, primarily to avoid the diamond problem. Shown on the right is the illustration that depicts what went wrong if the language supports multiple inheritance. So in that case, you can see that the employee customer class have no means of differentiating between the inherited methods with the same name that coexist in both the superclasses. So to avoid such problems, Java language adheres to the single inheritance model. Now another way to achieve inheritance in Java is by making use of interfaces. Think of interfaces as defining the specifications that the classes must implement in order to be fully compliant. Here you can see that we declare a couple of methods in the vehicle interface, and this differs from the class in a way that we are not providing the concrete implementation of these methods over here. We only specify the method name and its signature in the interface, and it's up to the classes that implement this interface to come up with their own implementation of these methods. So in this case, the bicycle class will implement the methods the way it works for bicycle, and the same is true for motorcycle as well. Once a class implements an interface, it is bound to provide the implementation of all methods declared in the interface. There is no way to escape out of it by implementing few methods and left others unhandled. Let's now switch to the IDE to see these interfaces in action. I have created a new project named interface and create a class main within that holds a single method named main that wraps our executable code. We created an interface named iBicycle. The initial I in the name reflects that it is an interface, though it is not required to name it this way, but it is considered a good practice. To create an interface, right-click on the source folder. Under New, click Other, type Interface, select Interface and click Next. Name it and place it inside some appropriate package, and this will create an interface for you. Next, you have to declare all methods here without the code block and end each statement with a semicolon. Then we create a class bicycle that implements the interface by using implements keyword after the class name and is followed by the name of the interface, iBicycle in our case. Now we are bound to provide the implementation of all methods declared by the interface inside this class. Another thing worth noting here is that since we interpret the use of the interfaces in the context of inheritance, We can do the casting operations for interfaces as well, the same way we did for superclasses. Now let's talk about some of the most commonly used classes in Java. The first in the line is string. There are two ways to create a string, a shorthand version and a longhand version. Choosing one over the other is merely a personal choice. As I stated earlier, in order to compare strings or any other complex object for equality, we have to consult the enriched API of these complex objects instead of using the math comparison operators. So to compare two strings, equals method from the string class will come in handy. Likewise, we can get the length of the string by using its length method. It returns the count of the number of characters in the string. And also, we can break apart a string into individual characters by looping over the string and using the char at or car at method, however you pronounced it, to get to the individual characters by its index position. You can concatenate two strings. The concat method returns a new string altogether by adding a new string to existing string represented by str1 in this case. If we were to extract a substring out of a string, the substring method from string API is worth looking at. It has a couple of overloaded methods. Please refer to the string API documentation for more details. Furthermore, strings are immutable. It means that once we assign it some value, it will never get changed afterwards. It seems that we can do so by assigning a different string altogether. But what actually happens in the background is a new string gets created and the old string is dereferenced and hence available to be garbage collected. So if the requirement is to make changes to an existing string a couple of times during its lifespan, the sensible choice is to use the string builder class in that case. The API of this class exposes some useful methods that basically facilitates the developer to insert string anywhere inside an existing string without creating a new instance each time we need to make changes to the string. Another common complex object used more often in Java is the date object. When you declare a variable with the date data type, you get a squiggly line under the date keyword, signaling that the compiler does not recognize the keyword. The reason, as I stated earlier, is that only classes from java.lang package are available to the code and to the runtime. For all other classes, we need to step into the other packages from Java core and explicitly mention the package in the form of imports. Since date belongs to java.util package, the import should be right there at the top. Constructing the date from a no argument constructor returns the current date and time on your computer. In order to construct a date class, the date API exposes a couple of constructor methods that are worth looking at. Another way to work with dates is to use another class from the java.util package named Gregorian calendar. Use this class when there is a requirement to do math operations on date. You can see here that we are instantiating the Gregorian calendar object with three arguments constructor method representing year, month and day, with month part starting from 0. So 0 is January, 1 represents February and so on and so forth. Then here we are adding 5 days to the day part of the object. And since Gregorian calendar does not have any formatting of its own, we have to extract the date out of this class and then format it using another complex object from Java core named dateFormat. This class facilitates us to format the past in date. Instead of using the new operator for creating objects, here you can see that we are requesting the dateFormat class for its instance. This class basically implements a factory design pattern, and this pattern dictates that the methods of the class will take the responsibility of providing you with an instance of that class. Later, calling the format method on the date will return back the formatted date. Run the program and you will see the results of all we discussed so far. Errors in Java are classified to be either one of two types: compile time errors and runtime errors. Compile time errors are the ones that can be caught at compile time and are most commonly the ones that breaks the Java rules. Like here, you can see that this statement is causing an error. depicted by this red circle with cross inside. And when you hover over it, it says that the statement is missing a semicolon. And by inspecting it, we realize that we are not terminating the statement with a semicolon. Adding it to the end will resolve the problem. But the runtime errors are the ones that are syntactically correct and will only get emerged and breaks the application at runtime. To anticipate runtime errors that might have originated during the code execution and to elegantly deal with it, Java provides us with a try-catch construct. So all the offending code that may cause the application to break will be wrapped inside the try block, and the subsequent catch block will then catch the exception that was passed in as an argument in case something went wrong in the try block. So each time an error occurred inside the try block, the JVM creates a new exception class or one of its subclasses, filled in the error relevant details and provide as an argument here. Here you can see that we are creating an array with two elements and then later refer to its fourth element. Since the array is defined to be of size 2 and we are requesting the element that exceeds the array range, the JVM reports an error by packaging up the error details inside an appropriate error class and pass it as an argument to the associated catch block. Run the program and you will see the results. Here you can see that the JVM throws an exception class of type array index out of bound exception from the java.lang package. Since all exception classes in Java are extended from the superclass named exception, so we can catch more specialized exception classes into a more generalized superclass to benefit from its polymorphic behavior. So finally, we are reaching to the end of the course. Oh, I would like to thank you for your time to watch it to the end and hope that this course takes your understanding to the next level. Before I say goodbye to you, I would like to request you to please subscribe to this channel for latest updates. Goodbye and see you in the upcoming courses.